Good afternoon to all, and a warm welcome at the Sfen. On Tuesday, 3rd September, at 3:54 p.m., Flamanville 3 achieved first criticality. Today we are hundreds on the line to celebrate this first criticality and to share operational and technical information about this event. Last May we had a webinar just after the fuel loading at Flamanville 3. And in January 2022, we had already gathered to celebrate the commissioning of OL3. With this fourth reactor starting up, the EPR family journey is going on. Today, I have the great pleasure to welcome at the Sfen Gregory Heinfling from EDF. He is the Flamanville 3 site director. Fabien Hensch from Framatome is the senior project manager for Flamanville 3. And Loïc Andries from Framatome, who is a Neutronics engineer. I will give them the floor very soon. Gregory will tell us what happened since the core loading and how the things are organized between the Framatome and the EDF teams. Fabien and Loïc will then recap how we got critical and what are some of the physical and neutronics tests that are performed at the plant. And afterwards, Gregory will explain the next steps. And after, we will have quite a time for question and answers. For that, for the Q&A, the questions are asked in writing in the system. You will, for that, find an application on the top of your screen, normally, which is Slido, with an icon like an S. And through that application, you can ask questions. Don't use the chat. If you don't have the Slido application, you can go to the chat, and then you will find the link to the Slido application. You can write questions, but also you can vote for questions already put through the system. And I will start the Q&A with the questions receiving the greater number of votes. And you can start now to ask questions. Without further ado, let's go to the plant. Gregory, tell us about this very much awaited step. What happened? And the floor is yours.
Thank you, Bertrand. Do you see the slide? Yes?
Yes.
Thank you. Since the fuel loading beginning of May, FLA3 has entered what we call its startup phase. So this phase is actually a step-by-step process that embeds an important commissioning program. It is driven in constant communication with the French safety authority. That's why, as you can see on the figure on the top of the slide, several milestones for approval are defined and are actually applied. This startup phase is subdivided in 4 sub-phases, which are called DEM phases, 3.1, 3.2, 3, and 4. And just to give you some global figures, we will perform on the overall 4 sub-phases, a little bit less than 200 test procedures. We will make some ground transient operational or incidental, turbine trip, partial trip to house load, reactor trips. And we will also perform an electrical sources switch. Since the beginning of the fuel loading, operating technical specifications are applicable and applied for any operations on the reactor. And in parallel to the test program that we performed, we of course are to perform the current operating of the plant. Just to give you other figures, we have about 900 outage type tasks to perform, to put the reactor in configuration for the different tests. We'll perform a little bit less than 400 periodic tests during this phase. and also a little bit more than 2,000 preventive maintenance tasks. To perform all the test program, we have defined an organization that we have fully tested during the previous global test period, during the hot functional test in particular that were done before fuel loading. And in these organizations, the responsibilities are shared in the main control room. Globally, Framatome conducts and performs the test according to the program, ensures the post-treatment calculation, and analyzes the conformity of the results with the design assumptions. EDF design and commissioning team ensures the supervision of the test and the conformity of their results with the safety criteria. EDF operating team, that is the future operating team already of the reactor, performs all the operation technically and concretely from the main control room or on the reactor on site itself. And they permanently checks its parameters with regards to the operating technical specifications. Before the first criticality, but that has been recently reached on Flamanville 3, a lot of work has been done within the framework of this test program. You can see on the two blocks on the left part of the slide the two first phases of this global program that were fully completed before first criticality. Our colleagues from Framatome will give you some detail about what has been done technically, but just to give you some global information. Some adjustments on equipments have been necessary. So the program was completed and globally fully satisfying the criteria. At the end, fully satisfying the criteria, but some adjustment on equipments have been necessary. Several operating procedures have been updated, completed, and fine-tuned. Some technical operating points not stopping the test program have been identified. They have been put under control by temporary measures, and final resolution is defined and is planned during further phases in operation or during further outages. Several significant safety events have also been reported and analyzed. They are spread on three main families of root causes: human factor, equipment reliability or design, and operating technical specification complexity. So I propose our colleagues from Framatome to explain new and more details what has been done technically during the critical test.
Thanks a lot, Gregory. And now Fabien and Loïc will tell us a little bit about the way to prepare physically, in physics, in terms of physics, to criticality and to get critical. The floor is yours.
Thank you. Yes, during the last months, a lot of job has been performed during this phase. Our teams perform all the commissioning tests required before criticality. We started, as it is shown by a first sequence with tests at cold temperature, such as the static and the dynamic venting of the primary circuits through the successive stacking of the motor pumps. We test also and commission the core instrumentation, what we call the aeroball measurement system. And we perform a lot of tests for the road position control and monitoring system, which is called the RGL, with three kinds of tests. First, we test the road. The 89 roads were extracted one by one from the core to check their operation. We also perform road time measurements, so RPI calibration test. At the end of the cold test, we reach a level of around 55 degrees and 26 bar. That allows us to measure the primary flow, cold flow. Then, as you see, we perform successive steps of pressure and temperature in order to check at different temperature, 120, 180, 280, intercalibration of primary temperature sensors.
Sorry, just
yes.
Can you check that the presentation is shared on my screen? I don't have it.
It disappeared?
It disappeared.
We will relaunch it.
Yes. Right.
Yes, that's it.
Okay.
Fine, thanks.
And then the rise in pressure and temperature continue up to 300 degrees and 155 bars in order to perform what we call the hot pre-critical test with the regulation test and core instrumentation and spraying test. It allows us also to check the proper functioning of the reactor through several transients, like the automatic cooldown by some safety valves, and also the shutdown of the pumps. And at the end of this sequence, which has been successfully performed by the end of August, the reactor was ready for diversions. We can see on the next slide, Gregory, that we entered in some weeks into what we call the phase 3.3, and one key operation was to reach the first criticality. So I will hand the floor to Loïc Andries, who will explain in detail how we reach such first criticality.
So on Monday, the 2nd of September, we received the authorization to the first criticality here in Flamanville 3. Because it's the first time for this reactor, the approach is really smooth and safe. So first of all, you don't see it on the plots, but we have to extract the safety and the control rods outside of the core. We only keep one bank. It's P1 in blue on the graph. We keep it halfway inserted on the core, and after that, we need to reduce the boron concentration. So we dilute the primary coolant during almost 10 hours. It represents 340 cubic meter of pure water. And after this dilution, we search for the criticality using the control rods. So what you see on the graph, the blue line, it's the P1 insertion in the core. And the peak that you see in the number 2, it's a sequence that we call in French, I'm not sure about the English word, but it's pumping. So in this process, we extract the control rod up to plus 75 PCM in reactivity. And if the criticality is not reached during the sequence, we reinsert the control rod to its initial position. And then we reduce a little bit the boron concentration with a small batch of pure water. So what you need to understand on the plot is that in terms of reactivity, the top of one peak is equivalent to the bottom of the next sequence. So it's a step-by-step process. What you see is that after 9 sequences, the criticality was declared in the control room by the core physicist the 3rd of September at 3 p.m. and 44 minutes. The first criticality, it's a big step for the project, but it's also the beginning of the zero power physics test. it's a big program of core testing. So we will calibrate the instrumentation, the nuclear instrumentation, and also we will put the reactor in multiple configurations, moving the control rods, also adjusting the boron concentration and modifying the temperature of the coolant. The objective of the zero power physics test is to measure a lot of core parameters and to compare them to the theoretical values that we have calculated in the engineering office. So among those parameters, we have the critical boron concentrations, we have the temperature coefficient, or also the Hodsworth. Only during the zero power physics test, we have a specific device. It's called the reactimeter. So it's directly connected to the nuclear head core instrumentation, and it calculates in live the reactivity inside of the core. So it's dedicated to this zero power physics test. We don't use this in a normal operation. And a few words about the team. So Framatome have a team of 20 core physicists, only for the zero power physics test. So we are well trained on simulator since a month ago, and we have the benefits of the experience because a lot of people of this team have already done the first startup in China, and in Finland. And I have chosen to show you one test that we did last week. It's an example. It's the measure of the isothermal temperature coefficient. As you know, the reactivity is affected by the temperature inside of the core. So we need to measure the isothermal temperature coefficient to know how the reactivity is affected by the temperature variation. Also, it's important during all the physics tests, we need to control the neutron flux inside a specific range. So during the measure of the isothermal temperature coefficient, first step, we insert a groove. Here it's P1. And so the reactivity becomes negative, and the neutron flux in green will decrease. A few minutes after that, we start the cooling process using the pressure set point on the secondary system. The temperature will decrease. So because of the temperature coefficient, the reactivity will increase, but at this moment, it's still negative. And so the neutron flux is still going down. We have a point in the middle where the reactivity is equal to 0, and the flux that was decreasing starts increasing. At the end of the cooling, the point number 4, we kept the temperature stable. So the reactivity is stable also, but positive. So the flux is still increasing, and we have to do a last step, the number 5. It's a rod insertion in order to have a reactivity around 0 ppm and to control the flux. So what you see at the end of the test, we have temperature variation. We have the impact on reactivity, so we can calculate the isothermal temperature coefficient. And also, the green line on the graph, we control the flux inside the range that we wanted.
Thanks a lot, Fabien and Loïc, for this very smooth and clear and attractive presentation about the physics. It nearly looks easy. So thank you very much. So now the reactor is critical. The 0% power tests are performed or to be completed very nearly. What are the next steps, Gregory? What are the coming weeks and months made of?
So as we mentioned before, we still have an important commissioning program in front of us before to make the reactor fully available for the electrical network in France. During the current phase, as you can see on this slide, we will not only work on the core of the reactor, as was described by the colleagues, but we will also work on the secondary system and, of course, on the turbine itself. And after a few phases of test, once the turbine will be and the associated systems will be fully validated, we will reach an important step for Flamanville 3 that will be the first connection to the grid. That is planned once we have reached the 25% power stage of the reactor. As you can see, this test program comprised a lot of transients on the core and on the secondary systems, and that requires they will be performed for the first time. That requires from the operating teams as well as the commissioning team a lot of concentration in the control room, but also on the field. And also trainings are regularly and just in time performed for each of these transients on the simulator on site with a full team that train together. That's an important point in our organization. As you can see in the second part of this third subphase, we will once we have reached 60% power, we will perform the first ground incidental transients that for which we have to check that the reactor is behaving as planned. In particular, we will make the first reactor trip test of reactor trip plant reactor trip, a test of turbine trip, and a test of trip to house load within this phase. We will continue actually the test after after reaching 100%. So once we have reached 100%, fully connected to the grid, we will continue actually to perform some tests of the reactor, and we will once again check that it behaves correctly through ground incidental transient. And once more, we will perform a turbine trip, a trip to house load, and a reactor trip. And it's only at the end of this program, when this program will be fully completed and the results fully validated, and after a few hundreds of operating hours, that we will declare Flamanville 3 fully available at full power for the electrical network in France. So we will enter in the production phase of Flamanville 3 at this stage.
Thanks a lot. Thanks a lot for sharing those elements and the real life at Flamanville 3. So you have been perfectly in time, so we have plenty of time for question and answers. So I remind the procedures. You can for asking questions. We have to go through the Slido application, and normally there is an icon at the top of the screen with Slido. It's an icon with a kind of an S. And there you can type questions or vote for questions already put on the system. And if you don't have the application, it's according to the version of Teams you have, you can go in the conversation. Conversation is not to be used, but there is the link to Slido that you can use. So this is for the procedure. And now there is a first question to you about the results of boron concentration and rod positions to get critical. How close were they to the calculations? To the forecast?
So, as you saw on my first slide, we had to do 9 sequences to reach criticality. It's not the critical boron concentration was near the calculated value, but we had a criterion to stop the dilution, and this criterion was a little bit too high. So we had to do a lot of pumping sequences, but the critical boron concentration was near the measured value, the real value.
Okay, so if I understand well, you had to pump, if it's the right word, to 8 sequences or 9 sequences. It's not because the computation was not precise. It's because you really wanted a margin, quite a margin, towards criticality, in
Yes.
order to be absolutely sure to get critical with the rods and not with the dilution.
Yes, exactly.
And the computation themselves, if you had wanted to get close without those margin to the criticality, the computation were accurate. How accurate were they? Not the numbers, but were they close, or did you have to adjust the models?
If we had followed the calculation, we would have to we would have reached the criticality during the second pumping phase.
Very interesting. Very interesting. And I think this is a good accuracy for a new core, a larger core, where you can't expect the same accuracy than compared to the operating plants in the fleet. It's linked to another question afterwards. Do we fine-tune the models given the actual results? Is there a feedback loop towards the models in a way or another?
So you ask if we have to modify the models after the results?
Modify or fine-tune or take into account the real results to improve the model or fine-tune the computation? Is there a feedback loop towards the model?
Not for Flamanville 3.
Yes.
So we have the model, we have the calculated parameters with the model, and the purpose of those core physics tests is to verify that our measure are close to the model. And if it's okay, we only use the model that we did during the engineering design.
Okay,
it's the case here in Flamanville.
Okay, then we have on Slido a question which starts by congratulations. So congratulations again, really, it's what we share today. And the question is that was there something different, significantly different in Flamanville 3 compared to Olkiluoto or Taishan in terms of startup getting critical and core tests? Are there French specificities or Flamanville 3 specificities?
You mean specifically for the core behavior, or,
yes,
or more globally?
Yes, about the core behavior. What happened so far? Is there something different from the other reactors? Did we notice or do something different?
Just to answer, the test program is quite the same
yes.
as previous EPR first. Then during the two first phases, we have observed any unexpected results. And for the core test who just started some weeks ago, I don't think so also.
Okay.
Which is what is maybe different is what we call the STE, so the hotel.
Yes, it's clear.
So yes. It leads to different constraints compared to previous Taishan or OL3, for example.
Yes, you're right. Globally, so out of the core on the global reactors, the test program is almost exactly the same between Olkiluoto, Taishan, and Flamanville. We took, by the way, a lot of feedback from their startup to correct our test procedures or also fine-tune some equipments. What Fabien said is very important. We have to apply, since the fuel loading, the operating technical specifications, and they are significantly different between Olkiluoto, Taishan, and Flamanville. That's why there's in some cases the way we conduct the configuration changes, the way we correct potentially the fine-tuning of the equipment is submitted to some constraints that are very different, and that's why we for some cases take more time than in Olkiluoto or in Taishan, and in other cases it's the opposite. But globally, the program is the same. It's just the constraints that are imposed by the operating technical specifications that are different. Of course, each reactor has also its own history in terms of aging of the equipment and so on. So we sometimes faces some necessity of adjustment or anticipated maintenance that were not necessary on Taishan and Olkiluoto, or sometimes that's the opposite. But once again, we in advance took as much feedback as possible to correct that before we launched the startup phase.
Thank you very much. Very clear. So I understand that from a physics point of view, core behavior point of view, there was no significant difference compared to Taishan and Olkiluoto so far. No difference, no significant difference with the computing, with the forecast, and no real surprise. In fact, if I recap so far. About the surprises, in Taishan, there was something a little bit unexpected measurements involving the neutron flux fluctuation. So in Flamanville 3, where are we in terms of measuring and monitoring this phenomenon?
This phenomenon, we only see it with the power and with during the cycle with the fuel burn up. So at this moment, during the zero power physics test,
Mm-hmm.
We do some measurements, but we don't have all the parameters to estimate them at this point.
Okay. Okay. So very clear. So it's expected. It's monitored, but it's too early to see this phenomenon of fluctuation.
Yes.
And so it will be in the next steps that they will be precisely assessed and compared to the computation and to the other EPR behaviors.
Yes.
This is a technical question. This phenomenon seems to be linked to some vibrations, maybe or hydraulics vibration or fluctuation. Is there anything like this monitored, or is it through the flux that we see this phenomenon?
We don't monitor the vibration of the fuel assemblies in the core.
Mm-hmm.
So it's through the flux that we will see.
The flux. Oh, very clear. So it's through the flux and the modeling of what is happening that we come back to the root cause. That is some vibration of the fuel assemblies. Very, very clear. Thank you. Nice question also. Away from the technical and scientific aspects, let's go to the human side of the first criticality. At 3:54 on Tuesday, 3rd of September, in the EPR, at the plant, in the control room, what did you feel? What did you see? What did you hear?
I think each of the colleagues on the site has lived his own history, adventure with Flamanville 3. So each has felt his own sensations. But for everybody, it was a great moment, a great joy. Yes, you mentioned feeling of beating Earth. So beating Earth for the first time is like the birth of Flamanville 3, really. So I think it's globally, but for everybody, a very, very important moment.
Thanks. That even from far, it's quite a moment. So you can guess that inside the plant, it must be something. In the control room, it must be quite a strange moment, because there is the joy, the pride, and I guess you want to cheer, and also you have to keep concentrated and focused. So it must be a mixture of feelings and behaviors in the control room. What was the mood really in the control room?
You're absolutely right. Just before criticality was declared, concentration was above all. During, of course, 1 minute, there was a great moment of applause and joy. You know, in the main control, we have tried to preserve serenity during this phase. It's very important during all the phase anyway, but specifically during these specific and difficult transients. So 1 minute or two was applause and joy, and concentration came back very, very quickly, of course.
Thanks. And really a great question and great answer, I think. Another question, 20 core physicists. It's quite a team. It's quite a big number, and that's great. On the whole, beyond Neutronics, including all the aspects, how many specialists are working on the site for the commissioning in total? About?
You have a figure, Loïc?
Oh.
For the core physics, it's 20 people, but for the commissioning phase, we have a big team.
Yeah. If we consider all the colleagues involved in the commissioning, so it's about it's more than 1,000 people on site that are directly implied on site on these commissioning actions, either for operating or for checking the results or for preparing the test. So that's order of figure.
Okay, so on Framatome side, we are around 200 people on site to support the startup phase globally.
200. And on the whole, compared to normal operations, so 1,000 people now, compared to normal operation, how many more?
In normal operation, we will be 600, 650 on site.
So it makes 400, nearly 400 people more for the commissioning tests.
Yes.
So that's a great number, a great answer. Those 400 include the 200 of Framatome.
Yeah.
It's the whole headcount or just EDF?
Oh, no, you have about 200 colleagues from Framatome and about 200 colleagues from EDF that are here specifically for the test, that won't that won't stay after the plant is fully in operation. So
very clear, thank you. So 400 people more just for the commissioning test, and half Framatome, half EDF. That's
and also colleagues from Arabel and the turbine are also part of the 400 more people.
Okay. Okay. So yeah. Rapidly after the first criticality, there was a trip, a reactor trip, a scrum, a shutdown, automatic shutdown. So it made the headlines in the news. Can you say a little bit about this event?
Yes.
Is it expected during startup to have such events?
Yes. As you saw, we had planned to perform 2 planned reactor trips at different stages, but this one came very, very earlier than expected. Actually, we are analyzing it in detail, but the main root causes are a human error. To perform the first test, almost the first test, first physical test that have been presented by the colleagues, we had to modify thresholds in the INC systems on 3 divisions, and the procedure required that once we have implemented the new parameter in 1 division, we reboot the division that allows to make it available again from a safety point of view, and only after this reboot to go to the 2nd division and then to do it again and then to the 3rd. What happened is that the 1st division was modified and colleagues went to the 2nd division without rebooting, and then to the 3rd division. Then the system detected 3 divisions unavailable, and then as planned, operated the protection of the reactor. So we are analyzing the root causes why it was forgotten to reboot. But what is interesting, what is positive in this unexpected reactor trip is that all the protections of the reactor have fully operated, have fully worked as planned. We have been able to check afterwards that all the orders planned for the protection of the reactors have been transmitted by the INC system. So that's the positive point. The second positive point is that we entered in the accidental rating just due to this and this was done really with perfect in perfect conditions by the operating teams. They really operated the plant safely, following the procedures, and with a great rigor. And we came back to the normal operating of the plant very quickly thanks to that. And we have been able to reconfigure the reactor in a good way, very quickly, and in a perfect safety ensured all along the operations, about 2.5 days after. So from something unexpected, we have learned first, we are learning a lot on the way we have to be careful and really follow the procedures during this sensitive phase test. But we have also been able to check that first, the reactor was behaving really, and its protections were behaving really as planned. That's positive. And also that the operating teams were ready to operate in such degraded conditions.
Okay, thank you. So it was not wished, obviously, although other trips are planned and wished. This one was not, but it appeared to be an opportunity to check both on the procedure side, the training side, and the system side, that things were in good order.
Yes.
Okay. And did you restart since that?
Yes. So second criticality was performed on Saturday morning.
Yes, at 8.
At 8. Yes, exactly. Following, I think, the same
process. Mm-hmm. Except that because we know that the critical boron concentration is the same that we have calculated.
Yes.
We could stop the dilution a little bit after, and yes. We only had 2 pumping phases.
Okay. Okay. So got very close on the second time on purpose.
Yes.
On purpose. So well done. And tricky question: do we expect more of those events, unexpected trips? Do we expect? Can we forecast the kind of number on average that happened during the startup of a new reactor?
Yes, actually, it's clear that we expect to have other unexpected reactor trips. We do all we can to avoid it, but it's clear that the feedback is that on Taishan 1, they experienced 10 unexpected reactor trips. On OL3 between 5 or 6, something like that. It's normal because we test the reactor, we test the procedures, we test the professionalism of our teams. So it's the aim of this test phase to correct what is not perfect now. So we expect, of course, to have either an equipment failure or procedure imperfection or behavior imperfections that we will correct. We took into account the feedback from Taishan and OL3 for each of their reactor trips. We took into account the informations to try to correct our procedure, to correct the fine-tuning of some equipment sometimes, to avoid these reactor trips. But each reactor has its own history, each team has its own history and its own imperfections. And it's, for me, normal and clear that we will have such events once, sometimes during.
Mm-hmm. If I remember correctly, it was the case in the fleet when the reactor first started, the 900 megawatt, 1300 megawatt, the N4 series. There were trips at the first startups. What is interesting, if I remember well, in Taishan, there were, as you said, around 10 trips on the first reactor, but then there was fine-tuning, fixing some defects, learning about the regulation, the secondary sign, and so on. So on the reactor 2, they could manage the commissioning with, I think, 1 trip or something like that, very low number of trips, because of the learning curve from one reactor to the other, which clearly shows that there is always some things to fix, to learn, and to fine tune in a reactor starting for the first time. I have a question, I think, asked by people who really know the stuff. When are planned the first radial and axial power measurements? Is it before the 25% and coupling to the network? When do they happen?
We will do a flux mapping of the flux in the core already at 0.1 nuclear power, and we'll do the same at 10, 25, and after that. So we will have all the data already at the end of the zero power physics test.
Okay, thanks a lot. Very clear. The mapping about axial and radial flux is performed at each level of power, starting at 0%. If I remember the history as it was told me, in Paluel, the first reactor, it was at 0 power or nearly at very low power that some radial flux discrepancies were measured, and that led to the discovery that some assembly were a little bit bent, and so it was at very low power. And really, it's important to see the mapping at very low power too. So that which is done, if I remember correctly. Yeah, there will be quite a time between this startup and the next EPR2 startup commissioning. It will be long. How do we plan to capitalize on the experience?
So for Framatome side, within the company, and we have a dedicated process to capitalize on lessons learned, which was powered before, and now it is embedded within the organization. We have also the opportunity of the UK program with HPC and CyberC, who are today progressing also well, to send some experienced guy to support also this program. That's the main level we have within the company.
It is a very similar by EDF with some capitalization documentations and databases, of course, but most important are the men and the people that have experienced this startup, and they are already driven either to HPC or to the preparation of EPR2 operations. And HPC is a good intermediate target to keep people really in good professionalism for these sensitive operations.
And I guess that in the team, the 20 core physicists of Framatome and the engineers of EDF, I guess that in those teams there are young ones or mid-career ones that will be still in their career with this experience for the startup of the first EPR2.
Yes.
I hope so.
Yes, we have a great part, because when we started to build Flamanville 3, we had to rebuild the competencies in performing tests. So we had not that much experienced colleagues. That's why the colleagues that are currently performing these tests are still very young globally. There are some reference people who are more aged, and I don't know if they will be able to follow up to EPR2 startup, but most of the people in charge at this time in EDF are pretty young, and they plan to continue in this very exciting job.
Great. I think it's a wonderful opportunity at the start of the career to have this experience. It can ground quite a whole career.
That's the same approach. Within the 20 core physicists, if we compare to the previous project, the team is larger, maybe five people more. It takes the opportunity during this project to speed up the training on the field of the newcomers in order to build this new generation for the future.
Okay, so you took the opportunity to oversize a little bit the team to train the new generation. So that's great. Back to some technical question. The measurement at 0% power, the flux measurements and mapping, with what kind of device? Is that the collectrons, the SPMDs, the aeroballs?
No, we use the aeroball measurement system.
Oh, okay, the aeroball, which is the equivalent in a very different technology of the RIC on the traditional PWRs. Okay, thank you. With the difference which it comes in the core by the top rather than by the bottom, which avoids any penetration at the bottom of the vessel, which can be an advantage in case of an accident. Last question, technical. In China and Finland, were there some other transients that were performed that are not planned on the EPR, Flamanville 3 EPR, because they have already been done elsewhere?
No.
So it's nearly the time now. A great thank you to you, to Gregory, Fabien, and Loïc, on behalf of the Sfen and on behalf of all the attendees. It has been a great moment to celebrate and to share. And congratulations again from everybody about this the great step forward. We wish you the best for the next steps of the journey towards the full operation, the 100%, the coupling first, and the big transients and the full operation. And thanks a lot again to everybody to be there. We are hundreds on the line to share, and there will be a replay. So the full webinar will be soon available on YouTube. Sfen has a channel on YouTube, and on this channel you will be able, and anybody will be able to replay this webinar. So thanks again to everybody, and wish you a good afternoon.
Thank you, everyone. Thank you, everybody.
Bye-bye.